I have decided SI hours. They will be Wednesday from 2 to 3 and Friday from noon to 1. And my office hours will be Monday from 2 to 3 and Thursday from 7 to 8 p.m. And all of those will be in Schilling 310, just down the hallway. If you want to join the group me for reminders and schedule updates, I have the paper up here. You can scan it before you leave today. And since we don't have school next Monday, office hours will be moved, and I'll put the new time and location for that in group me later on. So I hope to see some of you there next week.
Great. So you got your SI sessions for the extra hours that Logan will be holding for you. So they got those review sessions and the office hours. Our professional tutor has started her office hours as well. She hasn't sent out the actual hours yet, so once I get those, I'll communicate those to you as well. And then our math center, I believe, will start hours next week as well after Labor Day. So we have lots of different opportunities to get assistance with different parts of the course. So. Like I said, once I know for sure when the math center is open, I'll make sure that I get that information to you. And I'll also post it on Moodle, so it'll be up there. I'll get these hours posted on Moodle as well. I'm gonna take a picture of them so I don't forget what they are. And we got all that stuff updated on Moodle as well, so you'll have that as a resource going forward. And if you wanted to, can you shoot me that QR code through email? Yeah, and I'll post that QR code that he's talking about with the group me on Moodle as well, so that if you forget when you walk out today and don't get it scanned, you can go back into Moodle and get that scanned later. Does that work for you? Yeah, cool, awesome. Any questions at all over anything before we continue on our discussion with functions? We're good to go? All right, let's go then. All right, so we talked about power functions last time. Why are you doing that? There we go. Talked about power functions last time. We had those couple of examples that we went through kind of painstakingly. And we noticed that when the power was odd, it went from lower left to upper right. When the power was even, it had that U shape. And then we collected the domain and range for all of those types of power functions, right? So remember, power functions was like x to a power. That power needs to be a positive integer, but that's what we call it, a power function. And all power functions look like one of those two graphs, depending on whether or not it's odd or even. We also talked about reciprocal functions last time. Again, we had, and my graph shifted, my picture shifted in the background. But we had that hole there at 0. We refer to that as a vertical asymptote. We'll talk about more about asymptotes later in the semester. We also see that it flattened out near the x-axis, and like I said, this thing got shifted on me. But if the power on the bottom was even, it looked like this. Power on the bottom was odd, it looked like that. It flip-flopped, right, on the left-hand side. But again, all reciprocal functions look like that, and we collected that information as well. Basically, what we're doing right now is just building a library of functions that we can build off of for later. Okay, that's the whole goal of this particular section. So, continuing, let's look at root functions. We started talking about root functions just a tiny bit right at the end of class last time. We ran out of time. But we said that when we have square root or cube root or fourth root, the root part is what makes the denominator of the fraction for our fractional exponent. And what we're going to concentrate, just like what we did on the power functions and the root functions, we're going to concentrate on what happens with that denominator, and that's going to tell us a little bit about what's going on with the function. So again, to start, let's just start plugging some points in. For this first one, does it make sense to put any negatives in? No, because we can't do a square root of a negative, right? And keep it a real number. Okay. Okay. So let's just plug in 1, 4, and 0, 1. I'll plug in 4 and I'll plug in 9. And I'm picking, I'll call them good numbers here because I'm taking square roots and I just want them to come out nice. Okay. So when we put in 0, square root of 0 is 0. Good. Put in 1, square root of 1 is 1. Put in 4, what do we get out? 2. Put in 3, we get out, or excuse me, put in 9, we get out 3, right? So we'll have 0, 0, 1, 1, 4, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 would be off the screen a little bit, or off the grid a little bit. Would be about right there. And we get this graph that looks like so. For cube roots, we'll do the same thing here. Any issues taking the cube root of the negative number? No, we're okay with negatives, right? So again, I'll pick some good ones. And what I mean by good are just that the answers will come out nice. Let's do -8, -1, 0, 1, and 8. Cube root of -8 is -2, right? Because of the negative. Cube root of -1 is -1. Cube root of 0 is. Cube root of 1 is. And cube root of 8 is 2. Good. So plugging these in, we had -8, which should be 1, 2, 3, 4, 5, 6, 7. Oh, it's also off my grid. -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. So this way, continue that way. All right, and notice that if we had another even root like a fourth root, do you think it would look like the first one or the second one? We had a fourth root. You think it would look like the first one or the second one? The first one, right? Because again, you can't do a fourth root of a negative, so it's going to stop at 0, 0, if you will. It'll be a little bit steeper here and a little bit flatter out this way, but it'll basically have the same exact shape. If I had a fifth root, which one do you think it's going to look like, top or bottom? The bottom. Yeah, same idea. Okay? So let's summarize. F of x equals nth root of x is called a root function. And again, where n is a positive, we'll say an integer greater than or equal to 2. Again, we're collecting information about these different types of functions. The information right now that we're collecting basically is what does the graph look like roughly? What's the domain? What's the range? Now, in this case, it matters for both the domain and the range what the n is, right? There's a difference when we have n is even or n is odd, which is off the bottom of the screen right now, right? If n is even, what's the domain? Yeah, that's right. 0 to infinity. Good. The domain, if n is odd, is negative infinity to all the way to infinity, right? Because if I look at the graph for where n is odd, we have the graph where n is odd, we don't see any holes at all, right? It goes all the way to the left and all the way to the right. Yeah.
So with the graph bracket, does that mean 0 is not included or it is included?
The bracket always means it is included.
It is included.
Yep. Yep. And we can take the square root of 0. That's not a problem. So it is included. So the infinities will always have parentheses because infinities aren't numbers, right? They're talking about behavior. Yeah. So in this case, the bracket will be on there for the 0 because it is included. We actually have 0 on the graph for the x's. All right, what about the range? What does it look like for the range for the top one for if the n is even? Remember, range is y values. What y values do you see on the graph for the first one? What's the lowest y value you see? It's 0, right? The lowest y value we see on the first one is 0, and it goes to infinity. It does it pretty slowly, right? But eventually it'll get to infinity. When you're looking at the range, you want to know what the whole range of the y's are. So you need to figure lowest y value to highest y value. Yeah. So we're just trying to figure out what y values actually get hit. What about for the second one? Well, this is if n is even. Good. Yeah, so it would be negative infinity and positive infinity on that one. Again, takes a little bit of time, but it will go off to positive or negative infinity on that. The bigger the x's get, the flatter the graph gets, but eventually it goes to infinity. Questions on that at all? We're going to have one more type of function that will be interested in knowing what the graph of it looks like. We'll do that here in a second, but I do want to mention that a summary of all these graphs, a nice little summary if you're looking for a picture, in your textbook on page 168. I know it's an ebook, so, but it's right before the exercises in section 2.2. There's a nice, I know you can't see it really well there. There's a nice summary picture of all the different types of functions that we were just talking about. The power, the root, the reciprocal, okay? So if you want to look for a summary picture, I would look at the book. All right, so let's look at this next example that I have on here, where we have absolute value of x. This is the last one that we want a relatively decent picture for. This will be the last one that we're going to add to our library. Again, what does absolute value mean? When you plug in a number, what type of number do you always get out? Positive, right? It could be 0, but remember, if it's positive, it leaves it alone. If it's negative, it makes it positive, right? That's what absolute value does. Okay. So, again, if I just start plugging in some numbers, if I do absolute value of -2, we get 2. Then we get absolute value of -1 is, absolute value of 0 is, and of 1 it's, and 2 it's 2, right? Doesn't change them when they're positive. And notice that if we put in 3, we would get in 3, 4, we would get 4, 5, we would get 5, -3, we would get 3, -4, we would get 4, and so on up the line. And we're getting this V shape, if you will. So for an absolute value function, you get a V shape. One important characteristic of this V shape, if you will, is the fact that this makes it abrupt, sharp corner. That's actually a right angle right there. Okay, so it's not a nice smooth graph. It comes down and then it just abruptly turns. Okay, kind of thing you're going to investigate in calculus if you go on to calculus. We refer to that as a sharp corner, and that has a special, it requires special consideration. So we're not going to do anything with that. I just want to mention that that is an example of a graph that has a sharp corner in it. All right, what about domain and range here? Any number that you cannot take the absolute value of. Can you take the absolute value of anything you want? Sure, right? The rule is if it's positive, leave it alone. If it's negative, make it positive, right? No issues with that at all. So our domain here is negative infinity to infinity. No issues there. How about your range? What's the lowest y value that we see on the graph? 0. Highest y value? Well, there isn't one, right? So it goes off to infinity again. Is that okay? Okay. All right. So what we're going to do now is investigate a little bit what happens when we start putting some other numbers with these things. We're going to do much more of analysis of this later on in this chapter. Right now, we're just going to play around with sticking a couple of numbers in different places and see what happens to the graph. So the reason why we want this library of functions is to help us see what happens when we start changing things, right? So looking at this particular function, we have y equals 3 times the square root of x. What we're interested in this case is what I like to refer to as a base graph, or a base function, if you will. And what I mean by that is, if I look at this particular piece of it, I see square root of x, right? That's what I mean by the base function. And we know what the base function graph looks like. We just did that a minute ago, didn't we? Okay. So our base function graph, 2, 3, 4, 2, and 3, looked like this red one that I'm drawing, correct? That's what our base function looked like. Now let's think about what that 3 does. Remember that if I'm doing this in red so that I have the difference between what I'm trying to do here, just looking at the base graph versus the other graph. A minute ago, we said when we put in 0, 1, 4, and 9, we get out 0, 1, 2, and 3, right? What do we get now if I put it into 3 times the square root of x? What is that 3 going to do to all these numbers here? Yeah, just multiply by 3, right? So I get 0, 3, 6, 9 for the outputs, don't we? Instead of getting 0, 1, 2, 3, we're multiplying all by 3, so we get 0, 3, 6, 9, right? So the points that we would have would be, here we have 3, here we would have 6, here we would have 9, and we would get a graph that looks like that, right? So looking at the graph, it's looking at the comparison of these two graphs. Did the graph get taller? Did it get flatter? Taller, right? It basically stretched it up, didn't it? So when we multiply that 3 on the outside, we ended up multiplying all of the outputs by 3, all of the y values by 3, right? So that 3 out in front made the graph 3 times as tall. So notice we didn't have to redo all. I mean, I did redo the numbers, but I didn't really have to redo the graph, right? I took my base graph that I knew what it looked like and just stretched it 3 times as tall, and then I got the new graph. This is why we want to build up that library of base graphs, right? This library of functions that we can deal with and then manipulate them into new ones. Let's see if we can do another one. This one looks similar, except we've got a negative sign there. We'll handle the negative sign second. What do you think is going to be the base graph here? Which graph do you think we want to use for a base? Do we want to use a power function? Do we want to use... Yeah, the absolute value function is going to be our base graph, right? And the graph of that looked like what again? A V shape, right? Good. I think somebody said V shape earlier, but yeah, I just want to make sure we're all on the same page. So again, this one right here, that's what we're going to use for our base graph. So our base graph will be this V shape. Okay. And again, I'm not looking for perfection when you're drawing by hand by any stretch. I want general idea. So on a quiz or on an exam, if you're doing a graph and you don't think you've conveyed what you're trying to do with the picture, write it out in words what you were trying to do. That's okay with me. Okay. I'm not an artist by any stretch of the imagination. Okay, so I'm not expecting perfection. I just want to know that you understand the idea of what's going on. Okay. All right. So in this case, we have to worry about two things. I've got to worry about this 1/2, much like what we worried about the 3 in the previous example. But we also need to worry about what this negative sign does. Okay, so we've got to worry about both of those things. First, let's just worry about the 1/2. Okay, let's ignore the negative sign for the time being. Let's just worry about the 1/2. Okay. Now, in the previous example, what did we say the 3 did? It made it 3 times as tall, right? So what do you think the 1/2 is going to do? Yeah, it's going to make it flatter, right? It's going to make it 1/2 as tall, right? Because we're multiplying all the outputs by 1/2. Okay. So this original graph here is your y equals absolute value of x graph. Let me change color to a different color slightly. So if I make it 1/2 as tall, this number was at 1, so I'll make it 1/2. This was at 2, I'll make it 1. 3/2, 2. So it flattens it, like so. And does the same thing on the other side. This would be y equals 1/2 absolute value of x. So just like we talked about in the previous example, that number on the outside of the function. What I mean by the outside of the function was, notice that 3 was on the outside of the square root. The 1/2 was on the outside of the absolute value. That's what I mean by the outside of the function. Multiplying that number on the outside is affecting the outputs. Outside, output, right? The first example, we multiplied all the outputs by 3. The second example here, we're multiplying all the outputs by 1/2. So that's why in the first example it got taller, because it was bigger than 1. Less than 1 made it smaller. Flatter. Okay. We still haven't handled the negative. Again, that negative is on the outside of the function, right? If it were on the inside of the function, in this case, it wouldn't do anything to the absolute value because absolute value kills off negative signs, right? Okay. So let's think about what that negative does. Again, it's on the outside, so it affects the output, right? So instead of the output being positive, then now the output's going to be negative, right? So instead of positive 1/2, we're going to be at negative 1/2. Instead of at positive 1, we'll be at negative 1, and so on. Negative 3/2, negative 2, negative 5/2, negative 3, and the same thing will happen on the other side. So we still get that same basic V shape, but now what's happened? It's flipped upside down, right? So multiplying by a negative on the outside of the function we say that's a reflex. We say it reflects the graph. It reflects the graph across the x-axis. Okay, flips it upside down. So a negative sign out in front of a function flips the function upside down. All we're doing so far is just dealing what happens on the outside of a function. Later on, we'll talk about what happens when we do things on the inside of a function. We're not going to do that today. Right now, we're just worried about what happens on the outside. And again, on the outside, it affects the outputs. Okay? Multiplying by a number on the outside scales the outputs by that number, right? Bigger than 1, it's going to make it taller. Less than 1, it'll make it flatter. A negative sign flips it upside down. So this one got flatter and upside down. Does that make sense? All right. Let's do this next example. Notice in this case, are we multiplying anymore on the outside? No. But again, what do you think we're going to use for the base graph? X squared, right? That's what we're thinking. What we should use for the base graph. I see x squared. That's the important part. Identifying that base graph tells us where to start. Okay? So, what type of function is y equals x squared? That was one of our power functions, right? And what tells us about the graph of the power function? What do we look for? Yeah, so the exponent, in this case, since it's even, it tells us that it's going to be a u, right? It's going to go this way. Right? Again, I'm not looking for perfection. I'm just looking for getting the general idea. X squared is a u shape. Goes up this way. Oops. Goes better than that. Flattens out of the bottom. I missed where I wanted to go. Missed it again. There we go. Better. All right. Here was y equals x squared. That's your base. Okay. In this case, the plus 1, again, is that inside the function or outside the function? Your base graph is x squared. Is that plus 1 inside the square or outside the square? Outside. And so anything on the outside affects the output. Okay? So in this case, we're going to add 1 to all the y coordinates. So what do you think is going to happen to the graph if I add 1 to all the y coordinates? You guys are going to move it up, right? I'm just going to take everything and shift it up 1 unit. Exactly right. So the graph's going to look the same. Let me change colors. The graph will look exactly the same, just moved up a unit. So it'll look like, I should flatten out. So this would be your y equals x squared plus 1. So notice if we add on the outside, it moved up. What do you think would happen if we subtracted on the outside? Move down. Yeah, exactly. So just to summarize that, adding a constant, no, I'm going to say add and subtract. Adding a constant on the outside moves the function up. Subtracting moves it down. I should say she moves the graph up. And then subtracting moves the graph down. We're going to, like I said, we're going to do more of this later in section somewhere along the line. 2.6. So we'll do more of this, more involved problems with this when we get to section 2.6. But for right now, you're kind of doing one at a time. What happens if you multiply by a positive? What happens if you multiply by a negative? What happens if you add or subtract a constant? Any questions on that at all? All right. So the next part is just a way we're going to build on this in the next section too. The next part is just a discussion of a visual way to tell whether or not a graph actually represents a function. And we refer to that as a vertical line test. So remember, when we defined a function, if I put one thing in, how many things are you allowed to get out? Just one, right? For functions, you put one thing in, only one thing can come out, right? So this is what where the vertical line test comes in. Remember that for a function, we associate input, comma, output as a point on the graph, right? So for example, if I look at this input right here, this is, well, I don't have good numbers on there to put it in there, but notice for this input, if this is my x, I've got two different y's that come out, don't I? Ooh, hey. Say if this is my y1 and this is y2 here. With this one x value, there are two y values associated with it, right? Agree? Yep. So notice that if I take a vertical line, let me try to do that in a different color, maybe. Why can I not get to where I want to go? If I take a vertical line, how many times did that vertical line cross that graph? Twice, all right? So would this be a function? If I think it as x is my input and y is my output, would that graph represent a function? No, they have two outputs to the same input, right? So that's not a function. And then we just did a vertical line there, hit it twice, right? More than once is the important part. Look at the next graph over. If I draw a vertical line here, how many times did that intersect? 3, right? 1, 2, 3. So this one input would have how many outputs associated with it? 3. So is that a function? No. Okay. So neither of these are functions. Why are you not opening up my menu? There we go. I don't know why it's being a pain. All right, so neither graph represents a function since we have at least one input that has multiple outputs. And again, we've got this visual way to check. I draw a line, a vertical line. If I can see a vertical line that hits the graph more than once, then it can't be a function. And so that's exactly what we mean by the vertical line test. So let's summarize that. It says a vertical line says that a graph represents a function if and only if every vertical line intersects the graph at most once. May not intersect at all, but if it does intersect, it can only intersect one time. That's what the vertical line test tells us. So what we have in the next is just some examples of which of the graphs represent functions. Let's look at the first one. Notice the first one is just made up of 5 dots, all right? Not a very interesting example, but it still illustrates the point. Notice over here, obviously the vertical line doesn't hit anything, right? Vertical line here would only hit one time. Here it would only hit one time. Here it only hits one time, but what happens at 1? It hits 2, right? Right? It only takes one vertical line to intersect more than once, and then you're just done. It's not a function, okay? So this is not a function here. It doesn't matter if it hits once sometimes. It has to hit once every time that you find a vertical line. Okay? In that case, we have one example where it doesn't work, so it's not a function. How about the next example? Function or not? No. Yeah, good. We've got lots of examples, right, of vertical lines that are going to intersect more than one time. So this is also not a function. The one here in the lower left corner, what do you think? Nope, that one's also not a function. Again, vertical lines over here in the middle don't matter because it doesn't intersect the graph at all. But if I take one over here or one over here, we've got issues, don't we? So then finally, what about the last one? That one's okay, right? If I take a vertical line here, or even there, or here, here, that's okay, right? And if the vertical line misses, that's not a big deal either. The vertical line test says at most once, right? All we have here is a hole in the domain, okay? So this one's okay. This one is a function. If I can spell, we'll write down that it is a function. So first three did not pass the vertical line test, but the last one did. Questions on that one at all? We're going to do more of that in the next section as well. Let's do an example or two here before we go on to the next section of how we graph piecewise defined functions. So we talked about what piecewise defined functions are. Let's just see if we can do a couple of examples here of actually graphing what they have to look like. So let's do I'll say the easier of the two things that you're being asked to do. Let's do the plug in the numbers first, right? If you want f of -2, which piece do you plug it into? The first one, right? So we would have -2 squared, which gives us 4, right? If you want f of 4, which piece do you plug it into? The bottom one, good. The second one, we would get 8. If we want f of 1, which one do we plug it into? The bottom one, and what's telling you that it's the bottom one and not the top one? Good. Yeah, it's the equal to sign, right? You've got to figure out which of those conditions your input satisfies, right? So I can't plug it into the top one because the top one says for only x's that are strictly less than 1, right? I don't want to plug 1 in there. I need to plug in 1 into the bottom piece. When we plug it into the bottom piece, we get 2, right? So we can plot, these all correspond to points on the graph. When we plugged in -2, we get out 4. When we plugged in 4, we got out 8. And when we plugged in 1, we got 2. Now, unfortunately, just playing connect the dots with these 3 dots isn't going to work very well for us for graphing this piecewise defined function. Something happens at 1 where the function changes definition rather abruptly, right? Okay. So we've got to handle each piece separately. So let's look at the first one. Let's just look at the first piece here, at x squared. What kind of graph does x squared look like? We just did that a minute ago. What kind of graph does x squared look like? Yeah, it's a U shape, right? We call those parabolas. That's exactly right. Specifically for quadratic functions, we call those parabolas. But yeah, it looks like a U shape, right? So if I were to just graph x squared, don't draw this all the way across like I'm going to do. But if I were just going to draw x squared, it would look like that, right? It would look like that entire green graph, wouldn't it? Do I want the entire green graph? No. I need to stop it where? At the 1, right? I got to stop it at 1. Okay? So when I graph x squared, change my color back again here. I'm going to graph my x squared coming this way and up to 1, but then I'm going to put a open circle there. It's going to stop. Why do I know it has to stop? Why do I know I can't have a filled in dot here? Yeah, so it's not equal to, and what would happen here if I had 2 black dots filled in? Yeah, I'd have 2 outputs of the same input again, wouldn't I? Right? So I know for a fact I can't have that point filled in there. It has to be open. So I'm going to get a parabola piece on the left-hand side. What's the right-hand side going to look like? If you graph something like y equals 2x, what kind of a shape do you get there? If I just have y equals 2x, what kind of a function is that? It is just a line, right? It has a slope of 2, right? So this piece is going to go that way. Notice it's going to stop here at 1, right? It can't keep going because, again, I wouldn't have a function anymore. So notice we're just graphing the two pieces individually and stopping it where we need to stop. So I graph the quadratic function. I guess we haven't called it that yet. We graph the U shape, the power function this way, and then we graph the line past it. Let's do the next one here. Same idea. Let's plug in the 3 points that it asked us to do. Which piece is the first one that -8 going to go into? Yeah, it's going to be the top one, right? Because the -8 is less than the -1 here. So we get 2 times the cube root of -8. Cube root of -8 is -2 times the 2 will give us -4. Which piece does the 0 go into, the top or the bottom? Bottom, good, because it's 0 is bigger than -1. So we'll get -2. Which piece does the -1 go into? The first one. Because again, that's the equal sign here, right? That's telling us it's going to the top piece and not the bottom. 2 times the cube root of -1. Cube root of -1 is -1, and so times the 2 will give us -2, right? Are we okay with the evaluation of these three? Now's the time to ask if we're not okay with the evaluation of these three. Okay. All right, now remember, you plug in an x, you get out a y. That's how we get points on functions, right? So that's how I'm getting my points that I'm plugging in here. We got 1, 2, 3, 4, 5, 6, 7, 8. -4, 1, 2, 3, 4 is down here. 0, -2 is here. -1, -2 is here. That's not a lot of helpful information to us right away, right? Because I don't know, I can't just play connect the dots when we do piecewise functions, because again, there's an abrupt change in definition, right? It's different to the left of -1 than it is to the right of -1. Okay, so we need to handle each piece individually, and that's where those base functions are going to come up for us. Let's look at this first one right here. What's the base function for that piece? Cube root of x, right? That's one of our root functions. What does that particular root function look like? Goes that way, doesn't it? All right. So I'm going to graph this up to, whoops, not all the way. Where does it stop? -1. It stops right here, doesn't it? I don't know. I want that rounded, not a line. All right. If I were to continue it, I'm going to do it in a different color so I can erase it here. If you were to continue it, it would continue to look like that, wouldn't it? Yes. F of -8. So for the -8, we want to plug it into this piece, right? Because it's less than. So cube root, if I ignore the negative, cube root of 8 is 2, right? So it's negative 2 for the cube root of negative 8, and then times 2 gives me negative 4. That's where it comes from. Yep. All right, so again, if I continued this, your graph would look like that, wouldn't it? For that root function. But we don't want to continue all the way. We want it to stop at negative 1. Okay. Let's look at the next piece. What's your base function for the bottom? The x squared, right? What does x squared look like? That U shape again, right? But in this case, since I've got a minus 2, what happens to it? It's shifted down 2 units, right? So instead of my U shape being up here, we're going to shift it down 2 units, and it's going to be here, right? Now, what's going to happen to this left side? Do I want to keep it going? No. As a matter of fact, when we get to negative 1, what do I want to put right at negative 1? An open circle. Good. I want to put another open circle right there. So notice again, we're using our knowledge of the base functions to help us get those graphs. And then since it's piecewise defined, I know I have to stop those individual pieces. Questions on that one? All right, let's see if we can do this last one and finish that off in the last 4 minutes that we've got. F of 0, oops, sorry, I want f of negative 3, f of a half, f of 2, f of 0, and f of 1. A little bit more complicated, but I think we can handle it. Which piece does negative 3 go into? The first one, right? Agreed? Yep. What do you get when you put negative 3 into the first one? You get 1, don't we? Absolute value of negative 3 is 3 times the third. So we get 1. What do you get? Which piece does 1/2 go into? The second piece, right? 1/2 is in between 0 and 1. So we would have 1/2 cubed gives us 1/8. Which piece did the 2 go into? The last one. And we get 0. Good. Everybody see why we're plugging this one into the first one, this one into the second one, that one into the third one? That's less than 1. That's less than 0. That's between 0 and 1. That's greater than 1. That's why we're plugging in those pieces. Okay. Now let's do the trickier of those. Which piece does 0 go into? The first one, right? Because of the equal sign, correct? Absolute value of 0 is 0 times a third is still 0, right? So we get 0 for that one. We plug in 1. Where does it go? The second one. Plug in 1, we get 1. 1 cubed is 1. All right, so just to plot these points, we have negative 3, positive 1, 1/2, 1/8. So we're kind of close to the x-axis there. 2, 0, 0, 0, and 1, 1. So far, so good? Okay. Now let's graph the 3 pieces individually. The first one, what's the base graph for the top piece? Absolute value. Good. What kind of shape does absolute value have? The V shape, right? Where are we going to stop it? Where does it stop as we draw? At 0, right? We don't want to keep going to the right, right? We want to stop it. What does the 1/3 do to it again? This makes the graph flatten, right? It's a third as tall. So I'm going to make a V shape this way until I hit 0. So it's going to stop right there, isn't it? We agree? Going to stop right there at that point? How about the next piece, the middle piece? What kind of function is the middle piece? It's a cubic function. It's one of the power functions, right? Since it's x cubed, well, how does it go? That way, doesn't it? Like that. Okay. But we only want the piece from 0 to 1, right? So of this, we only want a little bit, right? We want that little bit, don't we? From 0 to 1. I know it's not much. It's just that little bit right there. Finally, the last piece, negative x plus 2. What kind of shape is that? A line, isn't it? Well, it's not too hard to draw a line when I've got 2 points, right? The 2 points here. And I just go that way. Notice these pieces all connected up, didn't they? We didn't have any open or closed circles because they actually matched up. That happens sometimes. Any questions on that one at all? All right, so that one finished. That finishes up section 2. The assignment on section 2 is due on Thursday, I believe, the 5th. Yeah. Okay. So you've got a few days to work on that one. We'll get into section 3 on Wednesday. Remember, we don't have a class Monday for Labor Day. All right. Have a good weekend, everybody.